Welcome everybody to this week's feature, Rainscreens, Vikings, and the Evolution of Protection, featuring Dr. Joe Lstiburek. Brought to you by Casella Durkin, part of the Building Science Deconstructed series. Durkin has been in the construction materials business for 125 years, and we manufacture air barrier membranes and moisture protection systems for below grade. This is our plant at head office in Hedeke, Germany. Today's presenter is well known. It is Dr. Joe Lstiburek. He's the founding principal of Building Science Corporation. He earned his Bachelor of Applied Science in Mechanical Engineering, a Master of Engineering in Civil Engineering, and a Doctor of Philosophy in Building Science. The Wall Street Journal called Dr. Lstiburek the Dean of North American Building Science. His commitment to advancing the building industry has had lasting impact on building codes and practices throughout the world. Without further ado, I present the inimitable Dr. Joe Lstiburek.
Hello, everybody. Welcome one, welcome all. Peter, thank you for those kind words. I want you to know that I learned all of my building science from old people who took me under their wing and said, young Joseph, used to be young once. There's a lot you got to learn, and it's kind of nice to hook up with people that know more than you and spend a lot of time listening and learning. Today's chat is going to be with respect to the rain screen, and some of the stuff is going to sound very familiar to a lot of you, and others it might be new. There are really basically three different ways of dealing with rain. The first is what we'd call a mass wall, where just describe it, you've got a whole bunch of rocks or brick masonry all smooshed together. That's a technical term, smooshing together. And, around 1 to 10% of the water that's incident on the mass wall passes into the mass wall, and it's stored and redistributed and dries to both the inside and the outside. It's our oldest technology. It's quite impressive. It's not the best technology, but it's pretty darn good. The next type of approach is a face seal.
Excuse me, Joe.
Yes.
It's Peter. Can you please give us a little more volume? People are having trouble hearing you.
Well, okay, I'm going to stand closer to the microphone. I shouldn't have been using a Mac. Is that what you're telling me, Peter?
Well, I don't know if it's the technology or not.
Okay, so the next approach is a face seal system, where it's very common with panelized systems, structural glazing. Back in the day, it was face sealed synthetic stucco or external insulation finish systems. Basically, the approach was no amount of water was allowed to enter. So the first approach, mass, assumed entry and stored and redistributed and dried in both directions. The second approach said, hey, we can't have anything get in, and that to me is rather risky. I call it faith-based water control. And the third approach is called a drain system, and sometimes referred to as a screen system. That's where we assume that water enters, and that's a good assumption. And then the water that enters, we drain back to the exterior. And then we allow drying by having airflow and ventilation behind our cladding system. So it's basically a drained and back ventilated approach. And back in the day, it was called a screen. Today, we call it a drain. Sometimes we call it a rain screen. It goes by different names, but this is proven to be the most robust, the best way of handling a rain control. You don't have to be perfect, you just have to be good. And if you're good, chances are you're going to end up looking pretty damn perfect. The most important thing to realize with cladding systems is that all cladding systems leak. And cladding systems are much like people. As people in cladding systems get old, we leak. You youngsters have no idea here. I'm doing a simple experiment here with a garden hose. This person is clearly a Canadian. He's a hoser. That was pretty funny. In about 15 seconds, water begins to pass through the first layer of brick, the brick veneer. It doesn't pass through the brick. It doesn't pass through the mortar. It passes through the joints between the brick and the mortar. And what we've known over years is that between 1 and 10% of the water incident on the wall passes through the first layer of the cladding system. And the question is how do you deal with it? Well, first thing you have to understand is that we want to control the driving forces. And the most significant driving force is hydrostatic pressure. And a simple analogy is the taller the column of water, the more it weighs, and the height of the column of water exerts a force, and this force is called hydrostatic pressure. We measure hydrostatic pressure based on how thick the layer of water is. What's the height of the water? Well, it turns out that 1 inch of water weighs 1 inch of water. How much does 2 inches of water weigh? 2 inches of water weighs 2 inches. In most of the rest of the world, we use pascals. Pascal is a dead French guy, so 1 inch of water is 250 pascals. That irritated the English, so they defined a pascal as a Newton per square meter, and Newton is a dead English guy. So you had a dead English guy, a dead French guy, dealing with inches and units. So 2 inches is 250, it was 500 pascals, 1 inch is 250 pascals. So 1 inch of water is 250 pascals. A half an inch of water exerts the force of around a 35 mile per hour wind. So if water leaks into your wall assembly behind your cladding and it doesn't drain away, it can build up significant forces. So you can have more or less hurricane force loads on your wall assembly. In the absence of a hurricane, water just leaks in and doesn't drain away. If you drain the water away, you're eliminating the major force. And even if you have a hole, it's not much of a problem because there's nothing to push the water through the hole. This is a conversion of wind loading on a wall with respect to creating a force. And there's a nice conversion that basically shows that 150 pascals, it's about a 35 mile an hour wind. 250 is 45 miles, and 4 inches of water, 1,000 pascals, is 90 miles per hour. It's not unusual in a small space that's not drained to build up a couple of inches of water. So again, hurricane force loads can occur on a wall assembly if you don't drain the water away. So the magic is you need to drain the rain. And the key for draining the rain is to provide a drainage gap or a screen to allow the water to drain behind it. This is not a very good drain because we have mortar droppings. The mortar droppings prevent drainage and can create hydrostatic pressure. Now the question is, how big of a gap do you need to control hydrostatic pressure? The answer is not very much. Back in the day, we were asking for 1 inch behind brick, but that was because of a historic artifact. It's basically the thickness of Mason's knuckles and fingers. We can get drainage to control hydrostatic pressure in much, much smaller spaces, as we see. The old way of doing things was to put furring strips on the outside of a wall assembly. Typical furring strip is 3/4 of an inch, and that's because it's a 1x4. So, do we need 3/4 of an inch? The answer is, well, no, we don't, but we knew that 1 inch worked because it worked. We knew that 3/4 of an inch worked because it worked. could we get smaller and still control hydrostatic pressure? And the answer is yes, of course. We started playing around with things, and the smallest spacer that I could think of 20 years ago was a 3/8 inch strip of foam. We got foam sheets and 3/8 inch, and I cut them into 2-inch strips.
Excuse me, Joe.
Yes.
You're fading in and out a little bit. Can you move a little closer or speak a little louder?
All right. If I move any closer, I'm going to be eating the screen, but we'll try this. Okay.
Thank you.
Back in the day, the smallest practical material was 3/8 inch strips of foam I would take out of the support. You know, you get extruded polystyrenes. The thinnest at the time was 3/8 of an inch. So I started putting 3/8 of an inch on our drawings and papers, and people said, well, you know, Lstiburek must have done some work somehow. He came up with the 3/8 of an inch. And the answer is, well, it was what I could buy at the local lumber yard. There wasn't any research. That's what I got. Anyway, a bunch of people began to say, well, let's create more sophisticated spacing systems. This is a drainage vat behind what you'll see is cedar shingles and cedar siding. And the research was that, well, we did a lot of research and we found that 3/8 of an inch was the optimum thickness. And the answer is, well, no, that's what came out of their machine. But it worked. And how do we know it worked? Well, we put it up and let it be exposed, and sure enough, it drained. I mean, you think about this for a minute. I mean, how many nails penetrations do we have? We build with cedar shingles and cedar shakes. This is on Cape Cod. It's exposed to wind-driven rain, and we've got thousands of holes, but we don't care because we drain the rain in the gap behind the cladding. We have a rain screen that provides magnificent drainage. And again, if I don't have a buildup of hydrostatic pressure, I can live with holes. I mean, I'm going to have water, okay. I'm going to have a hole, okay. I now need a driving force. I'm getting rid of the driving force by draining the water away. So, and I can't tell you how important the control of hydrostatic pressure happens to be. So this is, this detail goes back almost 25 years. And again, the 3/8 of an inch simply was arbitrary and capricious based on what was available to me at the time. Could we go smaller? Yeah, we actually could, and we did. This is how you do it with continuous rigid insulation, with, again, a 3/8 inch space. But you still need a drainage layer that is reasonably free from holes, and that's the face of the rigid insulation with the joints tape. This is kind of neat. This is a crinkly building wrap, and guess what? It's a 32nd of an inch. Are you telling me we can control hydrostatic pressure in a space as small as a 32nd of an inch? And the answer is, well, yeah, you can if it's continuous. And there we go. So we went as low as a 32nd of an inch. My God. This is a 1960s technology. It's groovy. So there are many approaches to control hydrostatic pressure. The key is just to let the water drain away without building up hydrostatic heads. So we've got bumps, we've got grooves, we've got a gap, we've got lots of different ways of doing it. It just drain the rain. A guy that not quite as handsome as I am, but clearly as smart, I would argue maybe smarter, did his doctoral dissertation, and he was basically figuring out how low you can go by using washers to create a space. His name is John Straub. So Straub did some of the really, really neat stuff for his doctoral dissertation. So a lot of the numbers on drainage and grain stream effect came from John. So this is the basis of the theoretical, part of the theoretical basis for a rain screen. That led to some innovation on my part. I developed something called the beer screen. I found that if you could take the tops of, okay, this is meant as a joke. You're not supposed, don't do this, okay? This is not a lead-inspired technology, but the point is that there are many different ways of creating a gap to provide drainage. The physics of this go back to the 40s, and hence the Norwegian connection and the play on the words, Vikings. I guess Norwegians were Vikings, but Hansen was one of the first that started looking at the actual physics behind control of hydrostatic pressure and drainage and drying. And he was followed very closely by Neil Hutchins, Professor Hutchins. So we had some Norwegians and Canadians, more than a half a century ago, looking at the physics. But physics came after, way after experience. Believe it or not, the concept of draining assemblies goes back over 2,000 years to Vitruvius, BC, 10 books of architecture. So the concept of drainage goes back 2,000 years, but the physics of understanding it well only go back a little over a half a century. So the physics caught up to the practice, but there's lots and lots of experience with providing drainage. What we know today is how low we can go. We can go fairly small, as long as it's continuous.
So Joe, we have a question on that thickness. So Richard DeCampo would like to know if at 1/32 of an inch, doesn't capillary attraction come into play and negate the drainage potential of the gap, even with no hydrostatic pressure?
No, you're not going to get very much capillarity, maybe an inch, around an inch at that thickness. Now you go to a 64th or 122nd to get really small, you're going to be able to wick water tremendous heights with capillarity. I mean, the pores in concrete and wood are very small. You can get capillary rise in a tree to a height of 400 feet, right? The height of the tallest tree in concrete. God, you can go 10 kilometers, 6 miles. But at 32nd of an inch, we're talking an inch or two. It's, it's not a big deal. Not very high. No more difficult questions like that. Geez, he's capillary. Good question. So what did we do? What was the big improvement beyond the gap? Well, we actually put tar paper, a drainage layer, overlap shingle fashion behind our cladding system. And this worked remarkably well if you didn't have mortar droppings. So what's the point here? Well, we need a water control layer. We learned through experience that we need a water control layer in conjunction with the gap. So we need not just a gap, but we want a surface for the water to run down on the back side and the front side of that gap, hence the water control layer. And the traditional water control layers were basically originally building papers. And we developed more sophisticated synthetic wraps. And then we've gone to the spray applied and fluid applied systems, fully adhered peel and sticks, vapor open fully adhered peel and sticks, and taped foam sheathings. All of these provide a very, very effective water control layer. The fully adhered and the integral ones, I believe, are way better from a performance perspective than the mechanically attached ones, but you can still get pretty impressive performance with mechanically attached one. Anyway, bottom line is you need a drainage gap and you need a drainage layer, a drainage plane. And I call it a water control layer because the drainage plane came from dating my lovely wife, and we both love musicals, and we were watching My Fair Lady, and Eliza Doolittle says you need to drain. The rain in Spain stays mainly on the plain, and I turned to her and I said, you need to drain the rain on the plain. So drainage plane came from a bottle of wine watching My Fair Lady, and I said, oh, we should probably be more formal and call it a water control layer. So we need a water control layer and a drainage gap to control hydrostatic pressure, and we're good to go. Well, not quite, but we're almost good to go. What else do we need to know? Well, first of all, there are all kinds of ways of doing it. This is taping the joints or sealing the joints of gypsum, exterior gypsum sheathing, or coating it with a fluid applied, using tapes and sealants and fully adhere systems over gypsum board. We call this Barney because of the purple dinosaur effect. Huber zip, again, we want two things now. We want a water control layer and we want a drainage gap. Now we need a little bit more physics. Only a little bit more physics, not a lot. So if I turn a cup horizontally like this and it's raining, it's not windy, it's just raining. Now a raindrop falls into the cup. I can drain it to the outside because of the sloping surface of the cup. Not very sophisticated, but pretty darn effective. Then what? Well, let's assume that it's windy. If the wind blows into the cup and fills up the cup, if the wind can't get out of the back of the cup, I've pressurized the cup. So I'm not going to blow more wind-driven rain into a cup because the cup is already filled with wind. So it's kind of neat, turning a cup horizontally like this, you're basically pressurizing the cup if the back of the cup doesn't have any holes in it. If you cover most of the cup with a baffle and you still let air into the cup still is pressurized and the pressure is taken by the back of the cup. On the baffle, there's really no pressure. So water sitting on the baffle on the outside is not going to get sucked into the cup because there's no pressure there. We've equalized the pressure across the baffle. Now, real equalization doesn't really occur, but we call it as pressure equalized. It's really pressure moderated, but I'm not going to get into the arguments there. It's beer, wine, and a bartender with a physics degree is where you want to have that discussion. Well, how does this apply? Well, in typical glazing systems, we basically have an extrusion that has an inner seal and an outer seal, and we drain the space between the inner and the outer seal. The drainage hole provides two functions. One, it allows water to drain out because things inevitably leak. And the other is that it allows air to get in to pressurize the cup, or pressurize the extrusion. So you want a very, very tight inner seal, and the outer seal can age and fail, but you're not going to get pressure across it because I've pressurized the extrusion. So this is the classic way of doing glazing systems. Modern aluminum extrusions, modern vinyl extrusions, curtain wall systems, storefronts. It's the idea of basically an inner seal that's tighter than the outer seal. Well, we learned through experimentation and experience that we want the inner seal to be 10 times tighter than the outer seal. It's very difficult to make the inner seal perfectly tight. So we go out of our way to deliberately make the outer seal leaky by drilling more holes. So as remarkable as it seems, having more holes in the outside of this extrusion reduces the stress on the glazing system. So, and if you start off with a 10-to-1 ratio, the outer seal is going to age more rapidly than the inner seal. So it's going to get better and better as it gets older and older. And that's the argument I'm using in my career. Now that I'm older, I'm getting, okay, but we'll pass on that argument. Well, all right, well, we use the same approach with not just the window unit itself, but the hole in the building that the window is installed, the punched opening. So the idea is we have a 4-sided inner seal, we have a 3-sided outer seal, we have gaps at the bottom so that when drainage or when leakage occurs, we drain it back to the exterior. And we have this pressure moderated chamber. So we're basically doing the same technology of the curtain wall or the storefront or the window extrusion in the window to wall interface. Magic, absolutely stunning magic. But understand that the key is a 4-sided air seal. What we're trying to do is control the pressure across that space. And here are some of the technologies for your under window drainage and air control layer around the perimeter of your window. Peel and sticks, fully adhered, fluid applied, lots of ways of doing it. But here's kind of the deal. This pressure equalization only works for small spaces. So this idea of controlling the air pressure along with hydrostatic pressure, only works for small spaces. Hydrostatic pressure you can control over large air spaces. Pressure you can only control over small air spaces. So the idea is, well, let's compartmentalize our rain screen. Let's have a pressure equalized rain screen. And the answer is, in the real world, none of that ever works. So why? Well, okay, a little bit more background. The original concept for pressure control came out of two-stage joints with the precast industry. And a lot of the pioneering work actually did come out of Norway and Canada. But basically, you had a small chamber. You have an inner seal that's very, very tight, an outer seal that we poke holes in. So this idea of an inner seal, outer seal, two-stage joint, and you basically pressure relieve or pressure equalize across the outer seal. Worked really well for small spaces, small volumes, not big ones. And this is a section where you would actually tie in your outer seal to your inner seal to actually create a flashing effect at a vertical joint. Here's how four precast panels come together. This is kind of neat. This drawing comes to us from the 1960s. All I did was add color to an old black and white sketch. It's quite impressive. This was written down in things called books that were found in libraries. So you just have to go and read them. It's quite remarkable. But again, the magic was only for a small volume. Well, why? Well, it gets into one of the big arguments that we're having today, open joints versus closed joints. And I'm going to call it the limits of pressure equalization. This is pressure versus time. And for wind, I got news for you. Wind is not constant. Wind fluctuates. The wind pressures fluctuate very, very, very rapidly. And so the wind pressure fluctuation is a sinusoid. And what you want is, you want the pressure in the chamber to track the pressure on the outside. They need to be in phase. Here's the problem. Air is compressible. And in a large volume, the air compresses and it works out of phase with the pressure on the outside surface. So this pressure equalization only works with a small volume because of the compressibility of the air. So what ends up happening is, once you get past narrow joints, you're never going to get pressure equalization behind a cladding system. So the idea of, oh my God, I want a pressure equalized rain screen cladding system, these are from people who don't understand how wind actually works. It works for small volumes, not for big ones. Well, oh my God, if you now have an open joint system, isn't more rain going to enter? And the answer is, that's true, it does. But I have a huge impact on drying because I have more air circulation. The air circulation allows what? Drying. So I'm going to get more water in, but my drying potential increases an order of magnitude or two more than the rain entry. So, let a little bit of rain in, as long as you can drain the rain and then dry things out with back ventilation. Now, you don't want a lot of back ventilation, because if you do, you end up with a fire problem. So you want, Goldilocks, not too much, not too little, just the right amount. Anyway, so for pressure equalization to work, it needs to be almost perfect, and that only happens in a small volume. And pressure equalization reduces drying because it reduces airflow. And what we've learned is that the prevention of wetting is not as significant as the significance of drying. You assume that things are going to get wet and then design the darn thing to dry. So I'm a big fan of ventilated claddings because they promote drying, but not too ventilated because you don't want things to get out of hand. You don't want to have a fire issue. I mean, we ended up with a combustible cladding in London, England, with a 2-inch air gap, and that ended badly. If you're less than 3/4 of an inch, 1/2 an inch in that range, you don't have much of a fire issue because the friction the boundary layers is so great that you don't have enough air going through to support the fire. And this is, borne out by the NFPA 285 test. So not too big, please, bad idea. And in tall buildings, burn the wall, test it. NFPA 285, you ever see Jesse Beidel shake his hand? He was the godfather, the grandfather of NFPA 285. Wonderful guy. Anyway, what does this mean for aesthetics? Well, open cladding systems look cool. They're beautiful. I mean, architects, I don't like this ceiling and pressure equalization stuff because it looks like crap. And I'm saying, hey, let's get an open cladding and it looks beautiful and it works if it's not too open on the back side. And so I'm a big fan of drained and back ventilated claddings, but not too open on the back because we still have the fire issue to concern ourselves with. So the trouble with open cladding systems is they're open and you see through them. And sometimes you need something on the back to look good aesthetically and to prevent ultraviolet damage from damaging the rest of the assembly. So it's real important that you protect whatever's behind your open cladding system with something that is able to resist ultraviolet light and also provides aesthetics. So that's one of the issues that you need to address. And then there's one more, because there's always something. Remember Rosanna Dandana, if it's not one thing, it's another. Well, one of the things that we worry about with drained and ventilated cladding systems is if the cladding system is a reservoir. In other words, if it can get wet and store a lot of water, think of the cladding system as a moisture capacitor that is charged during the rain event. So it rains on brick, and I know you'll be shocked at this, but the brick gets wet. Then what happens? Well, if the sun beats down on the brick, it elevates the temperature of the water in the brick. What does that mean? It means that water wants to go from warm to cold and more to less. So there's more water in the brick than it's in the wall, and there's more water in the brick than's outside. So it's going to go out and it's going to go in. Also, the sun beats down on the brick, elevates the temperature of the water of the brick. It's going to be above the outside air temperature. It's going to be above the wall temperature. So we're going to get inward vapor drive driven by the sun and a concentration gradient. So we call it a thermal gradient and a concentration gradient. And the stuff that goes out, hey, we're happy about that. Yeah, that rock and roll. Now, if you paint your brick or your cladding system with something that doesn't breathe enough, it'll bubble and blister, and it's your coating system telling you you're an idiot. You picked something that didn't breathe enough. And what's a good number? Well, it's got to be greater than 10 perms. I like kind of 20. Between 10 and 20 seems to be something that will not cause the paint or the coating system to fail. What about the inward drive? Well, that's an interesting problem. We need some way of controlling that. One way of controlling it is to ventilate the hell out of the back side. Of course, if you ventilate the hell out of the back side, you need a fairly big gap, and you want to make sure that it's not going to be a big fire issue. What else can you do? Well, you can reduce the vapor openness of your water control layer in your sheathing. You can basically reduce the inward drive by putting a vapor throttle on the inside. Or you can put your reservoir cladding system over something that is more or less vapor closed and then back ventilate the space behind the vapor closed assembly. So, okay, where are we with all of this? Well, drain systems are absolutely the freaking best. And another name for a drain system is a screen. If you're going to have a rain screen, what do we need to do? Well, we need to provide control of hydrostatic pressure, so the screen has to be continuous. We also have to get rid of really big holes, so we want a water control layer, a drainage layer, a drainage plane. We can tolerate lots of small holes, but we don't want really big ones. So we want a water control layer with a continuous drainage system. And then finally, we have to deal with inward vapor drive, which is an issue with respect to reservoir claddings. And at the end of the day, we don't want the sucker to burn. So with that, I'm going to turn it back over to Peter Barrett, and we can play Stump the Chump now. And I would be the chump, and you get to ask the questions.
Joe, I've never been able to stump you yet, but we do have some good questions, and I'm glad you have this slide up because we have several questions regarding the space in the between the cladding and the sheathing. One person notes that the New York State Building Code, and I know other building codes as well, require a minimum of 1 inch with masonry cavity walls. Could they get away with less? And related to that is how much space is too much behind the siding. So it's really questions about the amount of space behind the cladding in front of the sheathing.
Well, you can go as low as a 32nd of an inch if you control hydrostatic pressure if it's continuous. We know that. We know that with bumpy house wraps. We know that from Professor Straub's doctoral dissertation, and we know it through experience. Where did the 1 inch come from behind brick? Well, it's a historic artifact. It's the thickness of a mason's knuckles and fingers. If attorneys laid brick, it would have been 3/8 of an inch. So that was actually quite funny, Peter. But the point is that you can get fairly small. Now here's a practical point. Even though I can get to as low as 1/4 of an inch or 3/8 of an inch with a drainage mat behind brick, I typically like to have at least a 1/2 inch because it allows the mason to straighten the wall out, right? Construction tolerances are not precise. And I like to give a skilled mason, a skilled bricklayer, the ability to move things around a little bit to make the darn wall look clean and straight. Just so. Now, you should ask me, Peter, how come the commercial requirements call for 2 inches, but the residential requirements call for 1 inch?
I am asking.
Well, again, it's one of those historic artifacts. Back in the 1940s and 1950s, we used to build cavity walls. And it was basically an 8-inch block wall with a 2-inch space and then a brick layer. So we have brick and air gap block. Now, back in the day, we laid out both of them, the block and the brick, from the inside without scaffolding. We'd actually, mason would set the edge of the slab and put up 2 inches or 2 feet of brick, and then put up 2 inches of block, or 2 feet of block, put a brick tie on top, another 2 feet of brick, another 2 feet of block, brick ties. And if we're doing it that way, there's no way of having a water control layer on the outside of the 8-inch block backup wall. So we needed to control mortar droppings. And so what did we do? What did the old guys use? A 2x4. We put a 2x4 in the bottom of the opening and hang it and pull it up every 2 feet. What's the thickness of a 2x4? 1.5 inches. You add a 1/4 inch on each side, and that's where the 2 inch came from. Now, that's also the reason why commercial windows to this day don't come with flanges. Residential windows are flanged. Commercial windows aren't, because we had no water control layer on the outside of the 8-inch block wall. The flashing had to go through the wall, had to go from the block across the opening to the outside face of the brick. You can't do that with a flanged window. Well, then what happened? Well, then there was this huge war between the masonry industry and steel studs. When steel studs came out, put up steel studs, gypsum board, you put a water control layer on the outside, and you had scaffolding, you could have the gap as little as 1/2 inch. But the steel people were unable to change the code. So the 2-inch space is a historic artifact from back in the day when we didn't have a water control layer on the outside of the masonry wall. Residentially, we had board sheathing, we had tar paper, and we had an air gap that could be as little as 1 inch because of the mason's knuckles and fingers. Now, the big trend today is to get flanges into commercial windows. There are companies that sell retrofit flange kits to attach to unflanged windows because they're freaking easier to water control. So you can go as low as a 32nd of an inch if it's continuous. The cladding system geometry will probably tell you, probably with brick, you're going to want maybe a 1/2 an inch to give people the ability to straighten it out as long as it's continuous. With certain places where you get an awful lot of rain, and you have stucco, for example, you're going to probably want 3/16 of an inch as opposed to a bumpy building paper. But if you're in Vegas, what happens in Vegas stays in Vegas, where you don't have a lot of rain, you probably don't need a big gap. So the gap can go anywhere from a 32nd of an inch to 2 inches based on the physics, the historic experience, and what type of water controlling cladding system that you have. The last little piece is, with inward vapor drive, you probably don't want to go less than 3/8 of an inch unless you throttle the vapor or the water control layer permeance and the sheathing permeance down.
So Joe, this relates to some of the other questions, and I think what you're trying to do right now is distinguish between a space for drainage and a space for ventilation, and now a space where you're expecting it to do both. Some people are asking, what about the space for ventilation as opposed to just a drainage?
Well, you don't need ventilation if you've got a non-reservoir cladding and you have a low permeance sheathing and a low permeance building wrap. So if I was to have, for example, OSB sheathing, and I have an integral water control layer on it, like a fluid applied or something like, say, Huber Zip, and I have vinyl or aluminum siding, I just, could get away with 32nd of an inch. I replace that with stucco, and I'm going to build in Atlanta. God, I'm going to need to have probably a 3/8 inch gap. I'm going to need to have some kind of a product. I mean, maybe black in color with dimples on it that you put the stucco of, right? Somebody should maybe invent that type of product, Peter. You got something in the bullpen. So you need a lot of back ventilation if you have a reservoir cladding and you have a vapor open sheathing and water control layer. If you don't have a reservoir cladding, you don't need the ventilation, you just need the drainage.
So where would you put the insulation in a reservoir cladding and a continuous insulation situation?
Well, I like having the perfect wall, right? So which by the way, I didn't invent, I just took Professor Hutchins' stuff from the 1950s and added colors to it, all right? And the argument is that he took it from the Norwegians, so whatever. So to me, I like, for example, steel studs. I like gypsum board, like dense glass gold. I like a fully adhered water control layer on the dense glass gold, maybe 2 inches of rock wool, and then something to provide UV protection and a small gap behind my cladding system, maybe 1/2 an inch. That's pretty darn good. If I replace the rock wool with oil-faced isocyanurate, I could go to whatever reservoir cladding I wanted. I wouldn't need any drainage at all, because if I'm driving the moisture in, it's going to condense on the outside face of the isocyanurate and drain out and call it a day. So what is my permeance of my continuous insulation? Do I have a reservoir cladding or not? And what is my insulation over? Those are the questions that you have to ask.
The additional question to that people have been asking is, what would the permeance of the water resistive barrier be in these situations?
Well, all right. So if I've got gypsum board is about 30 perms, and I can put a 50 perm fully adhered membrane over that or even higher. And I've got mineral wool or rock wool over that, which is vapor open. And I've got a brick veneer. I'm going to probably want to have half an inch to 3/4 of an inch to uncouple the brick from the inward, from the vapor open continuous insulation, the vapor open gypsum board, and the vapor open water control layer. If I now throttle the vapor control layer down to less than 10 perms, I could probably get away with less than a half an inch with a reservoir cladding. If I get rid of the mineral wool and I use extruded polystyrene, I don't really need any back ventilation at all. And I've gone from something that can be as high as 50 to 75 perms to something that can be as low as 1/10 of a perm. But if I'm at 1/10 of a perm, the thermal resistance of that continuous insulation now matters because I don't have to worry about condensation from the back side during cold weather. And so that's a different discussion. Maybe you can invite me back and we can argue that with Professor Straub. But the ratio of the thermal resistance on the outside to the cavity is very dependent on the climate location and what's going on inside. Big difference between a warehouse and an indoor swimming pool hospital museum in Minnesota versus Miami.
Sounds good. Another recurrent question is if you put up a water resistive barrier and you put a rain screen over top, you're now putting fasteners through your water resistive and air barrier. How would you address that, or is it an issue?
Well, if I'm controlling hydrostatic pressure, I don't care about the holes, and the holes from an air leakage perspective are trivial. So I wouldn't care. I don't care. I mean, I passionately and deeply don't care. Now, if I don't control the hydrostatic pressure, oh boy, now I care big time. And I gotta be almost perfect. Well, good luck with that. So if you control the hydrostatic pressure, the air and the water leakage becomes irrelevant. If I get rid of the big holes from an air perspective, no big holes. If you can crawl through it, put a body part through it, it's a big hole. The nails, screws, relax, take a Valium as long as I'm controlling the hydrostatic pressure.
So you've mentioned reservoir claddings numerous times. Could you clarify for people what you consider a reservoir cladding and what you don't?
Well, okay, brick is a classic reservoir. Stucco without paint, traditional hard coat stucco is a reservoir. Synthetic stucco is not a reservoir because it's got a lot of plastic goopy stuff in it, so it doesn't store. Wood siding is a reservoir, but you paint the back and the front, all 6 sides of the wood, it's a non-reservoir. Fiber cement, reservoir. The back and the front of fiber cement, not a reservoir. Vinyl siding, not a reservoir. Aluminum siding, not a reservoir. Glass, not a reservoir. Metal panels, not a reservoir. Did I mention wood siding? Reservoir. Ask me if I love wood. God, I love freaking wood. I love wood. But I know it's a reservoir, so I back ventilate and I drain it.
So another question we have is, what about vapor barriers in the systems you showed? You showed one with a low perm on the exterior of the sheathing. What about vapor barriers to the inside of the system?
I just hate vapor barriers on the inside of walled assemblies in all climate zones. Don't do it. You want to put a vapor barrier in your assembly, put it on the outside of your structure, and in a cold climate, put the continuous insulation on the outside of that vapor barrier. In a hot, humid climate, you're going to get moisture driven in. It's going to condense on the outside of that vapor barrier, which is also a water control layer. So, oh my God, I've got water on my water control layer. I'm going to drain it back to the outside. No vapor barriers on the inside of your framing in any climate in the world. Stop this. Stop it. Don't do it. It's stupid. I don't get invited to a lot of those conferences because of that opinion. I just happen to be right.
That's the...
Ask me if I came up with that.
Did you come up with that?
No. The folks in the 60s told me, but those people who lived in the 60s don't remember anything from the 60s anymore.
Do you have some thoughts on the lifespans of open joint claddings?
Well, you got to have stainless steel as your fasteners. And it's kind of important that if you're going to have a 50-year cladding, you're going to want to have a flashing and UV protection. It's going to be at least 50 years because it's kind of dumb to put a 25-year layer behind a 50-year cladding. That doesn't make sense. So you have to choose your UV protection based on the expected life of your cladding system, and just got to go to stainless, man. I mean, if you're going to do that.
Great. What about air spaces and fire? We've had several questions on that. Well,
there was work done, believe it or not, the National Research Council of Canada in the 60s. In 67, which was the last year the Toronto Maple Leafs won the Stanley Cup. I know. What can I tell you? I think it was Tamura and Shaw, George Tamura, and they were basically burning walls and found that once you got less than a half an inch space, or once you got less than a 1 inch space, the boundary layer friction on both sides of the cavity created enough resistance to flow that you didn't get fire propagation. And it was a very controversial statement because people were saying, "Are you telling me you don't need to fire stop things that are less than an inch?" And the answer is, well, yeah, the tests show that. But having said that, it's kind of dumb not to. Now, they were doing walls. That argument broke down when we started putting windows in those walls. And that's where NFPA 285 comes into place. And we find that, look, if you're less than 1 inch and you basically create barrier at the punched opening at the head of the window and the jambs, you're going to do well even with stuff that burns. You get down to a half an inch, and your risk is very, very, very small. And you get above an inch, and the risk is very high. Remember, Grenfell Towers, that was 2 inches, and they had a combustible cladding and combustible insulation, and it went up like a Roman candle. Now, let me tell you about EIFS. Now, expanded polystyrene, it freaking burns. But you put a very thin combustible stucco, with stucco lamina over it, there's no air gap, and the stuff doesn't burn. I mean, we didn't lose the Monte Carlo casino in Vegas, even though it had EIFS. The sign burned down at the top, but we didn't lose the cladding because there wasn't an airspace. So if you have no airspace or a small enough airspace, the problem goes away. Now, the problem without an airspace with EIFS, you have to do water management. So the idea is you have to put the airspace behind the rigid insulation. And the way that we all learned how to do that was that we would run vertical beads of adhesive, and when we smooshed the EPS against the sheathing, it left about 1/4 inch, and that was sufficient to control hydrostatic pressure, and it wasn't a fire issue. That's the long and the short of it. You get over an inch, and Danger Will Robinson, that was a 1960s television. Never mind.
That was Robot.
That was Robot B9, not Robbie the Robot. Robbie the Robot was from Forbidden Planet in the same year that I was born, 1950s.
So your comments on hating vapor barriers everywhere has given rise to a series of questions. Some around the fact that many codes in climate zones still require them, Some people want to know if there's climate zones where it should be to the exterior, and other people want to know about variable permeability barriers in that position.
Okay, well, let me first of all tell you that in the American codes, IBC, IRC, no climate zone requires an interior vapor barrier. I know that because I changed those codes. It took me 20 years. So my big success is you are not forced to put an interior vapor barrier in any of those climate zones in the United States.
But Canada?
Canada, yeah. The irony is that the work that I use to argue against vapor barriers in the United States came from Canada, and the only people that don't listen are Canadians. I don't freaking get it. My idea is the way to build a wall in a cold climate like Canada is to have steel studs, gypsum board, a vapor barrier on the outside of the gypsum board, and all of the freaking insulation outside of that. And then when the windows leak and bad stuff happens, the wall can dry from the vapor barrier to the inside, and we're good to go. Now, what about I'm in Miami? I have a brick wall, and I got rock wool or mineral wool, and I've got gypsum board on the outside. Is that too vapor open? And the answer is yeah. You're going to need a vapor throttle on the outside of the gypsum board behind the rock wool. And we did a lot of work. We want to be between 5 and 10 perms with a reservoir cladding and inward drive and a hot, humid climate in the building that's air conditioned. All of this is on our website, by the way, buildingscience.com. It's for free. And, Building Science Insights, there are 120 of them. And the one you want to look at is hybrid assemblies and how you decide vapor throttles. I've got a ASHRAE Journal paper going this month that's got 25 wall systems that are rated for all of the climate zones in Canada and the United States. They're all building code acceptable in the United States, but in Canada you're going to need an engineer or an architect to seal it to accept the liability. Of course, I might come back and retire in Canada and spend 20 years trying to change the Canadian codes.
That'll be the same year the Maple Leafs win.
Oh, don't make me cry, please.
So, Joe, we're coming up on 2. Do you have any final words before we close?
Drain the rain, baby. Drain the rain and vent with the reservoir cladding. Drain and vent, or drain and uncouple the reservoir with a condensing surface. Remember, over 2,000 years of experience give us this answer. And if you ever see me at a conference, let's have a cup of coffee and a drink together. I love all you guys and girls. Talk to you later.
Thank you, Joe. Let's see if I can get my own screen back here. So thank you very much to Dr. Lstiburek. We always appreciate your wisdom. This presentation was brought to you by Durkin Systems, manufacturers of the brown with the orange stripe, the well-known Delta MS, the foundation protection system. We also manufacture the engineered rain screen, Delta Dry, available as Delta Dry stucco and stone with the factory attached mortar screen, and the newest version, Delta Dry and Lath, that has the factory attached lath for your scratch coat. Saves you time, saves you money in the attachment. This is a project we did in Lockhart, Texas, the home of barbecue. This shows Delta Dry and Lath being used with Delta Vent SA, our fully adhered air and water resistive barrier. We have a little video on our Durkin YouTube channel. You can see how that was installed. Our next live webinar will feature Andrew Oding from Building Knowledge Canada. It's entitled A Solid Structure, starts with a solid foundation. This will be all about keeping your basement dry. Additionally, if you can't get enough of Joe, we have a series of videos. If you go to our website and go to Delta Academy, we have a full series of A Cup of Joe, where Joe gives his thoughts on all sorts of aspects of building science. The latest one up there this week is talking about the second law of thermodynamics. Coming up soon, we will have one featuring the continuity of control layers. Thank you very much for joining this webinar, brought to you by Durkin's Building Science Deconstructed. Have a good day, everybody, and stay safe.